so let's see. Let's move on to the next problem, and next problem is dealing with the spring, and which is very important for many reasons. So the problem said, let's write the formula first. The formula said spring, force of spring is simply kx, right? And with this formula we'll be able to find the potential energy of that spring, which is just this integral of kx dx, which is Pe. You're going to put the k outside, x dx. So Pe is just k, integral is 0 to x, which is square of 2. So Pe is half kx square. So potential energy of a spring is half kx square, half kx square. Now we can erase that. That's how we can derive the potential energy of a spring. So let's write some problem to solve it. Okay, so let's do this one first. All right, so say a spring. So a spring suspend suspend an object and 10 kg mass with 200 Newton per meter for 10 200 Newton per meter, and stress and stretches 0.3, just 3 centimeters. Okay, find force of a spring. Okay, so what is the stretch? Let's try to understand that. If there is a spring, right, the full, then x is no stress, 0, and if there is someone pull it and then it is stretch, and then the Fp is some kind of positive, and then if compress, then this is our x, and if stress, then this is our remaining x. In this case, is stress 3 centimeter. So stretch how much? How many meter? 3 centimeter. 3 centimeter is how many meter? 0.3. Well, I guess 0.03 meter. I guess. Okay. So let's solve it. Fs equal to k is 200 Newton meter times, I guess, 0.03 meter. Okay, so 200 times 0.03 is 6. Fs is 6 Newton meter square. What is Newton meter square? Let's see. Newton is simply kg meter per second square, and let's see. So so 6 Newton meter square. So let's see. kg meter per second square, and then you have meter square. Alright, so we're gonna keep the unit like that. Okay, so let's solve the next one. Next one is potential energy. All right. So potential energy is okay. So let's say we can make a question. All right. So let's see. If you pull well, okay, so a spring for 3 centimeter. If you pull a spring 3 centimeter, this requires I guess 75 Newton. Now if you pull a spring 3 centimeter, requires 75 Newton. And if you push same spring it also requires 75 Newton. Find how much work done, if stretch, and how much work done if compress. Okay. All right. Okay. So let's see. All right. So we know that F is kx hold. We know that the force of a spring is just kx, and k is constant, and x is the length of a stretch or compress. Okay, we got that right. Now we know that it holds each point enclosed. So F max is actually K max. All right. So F max, the force of max happens when the spring is stretched all the way or compressed all the way. So that's where the X max happen. In fact, we can use that to get the constant. So the constant is actually X max, F max. All right. So F max takes 75 Newton, and X max it takes 3 centimeter, which is 0.03, I guess, meter. All right. So Newton is 75, Newton is meter, Newton is kg meter per second square, and then this is 0.03 meters. Okay, so meter cancel, what we gonna left with? Kg meter per second square, and that's right. So 75 divided by 0.03, which is 75 divided by 0.03, which is yes, wow, 2500 Newton meter, right? So this is we're not gonna cross that. We're gonna say this is Newton and this is meter. So 2500 Newton meter. Okay. So let's see then what would be the potential energy of that spring. So potential energy is half K is 2500 Newton meter and X is 0.03 meter square. Alright. So now okay, so 2500 divided by 2 times 0.03 is 37. So 37, you have Newton is kg, then meter second square, and then Newton meter, and then meter, and then meter square. Okay, so meter cancel. So 37 kg meter square second square. So 37 kg meter square second square, which is just joule. Alright, so 37 joule. Alright, so it force potential energy is 37, actually 37 joule. Now let's see 37 joule. Right, so when it is stretch, it is 37 joule. When it compress, let's see what happens when it compress. So f of s is actually kx, and then we're going to integrate it from 0 to 0.03, and then it's going to be k. Well, you know, if we integrate it, this is dx, and then half kx squared 0 to 0.03, half k is, we already know what is k, 2500 Newton meter, and this is 0.03 squared and negative 0, which gives us 37 joule. So we know that if you stretch, the force of a spring is 37 joule. If you push it to compress it, again is 37 joule work done. So the work done is the same regardless you pushing it or pulling it. Why? Because when you pull, you have to exert 75 Newton, and when you in order to stretch it for 3 centimeter, and when you push, you have to exert 75 Newton to when you have to exert 75 Newton to push it, to compress it, well, I guess 3 centimeters. So the work done is same regardless you pushing it or pulling it.